Well, summer has finally arrived here in the UK after a slow start to the season, so it's nice to enjoy some hot sunny days in the garden again. And it's also hotting up in the workshop as I begin my learning journey into pouring hot metal to make my own engine castings. Welcome back to the shed. I've always wanted to make my own castings, and a few years back I made an electric furnace, but the heating elements kept falling out of the slots, so I tried some high temperature glass rods to retain the elements, but on the first test they just melted into a goop at the bottom of the furnace, so I shelved this idea until it could be resolved. Then, a few months ago, I saw this gold melting furnace, which looked like it would be ideal for melting alloys and casting some engine parts. I started with my pile of scrap aluminium that I've been saving for years, and started making ingots ready to go back into the melt. Now, I would like to start making engine cylinder castings, such as these from the Rob Roy Loco, but I will be starting with lower temperature metal rather than bronze or brass. I did a bit of research, mostly on YouTube, to learn how to make the two-part casting patterns. This was my first pattern, but I soon learned that it needed improvement, so my next version had an extension on one end to allow for easier work holding in the lathe for later machining. The two end protrusions are what is termed as a core print, and this is to allow an impression in the sand which will hold a sand core to create a hole through the cylinder casting. The two halves of the pattern are located via a couple of dowel pins, which align the two halves accurately. To make the pattern, two pieces of beechwood were glued together with a sheet of drawing paper in between. This will allow the pattern to be split open after turning. One of these furniture nut inserts was then fitted to the end of the block to allow tailstock support, and then this was held with a 4-jaw chuck at the other end in the lathe for turning. The registration of the split pattern is achieved with two dowel pins. Now, to get the pattern alignment, the block was marked up where I wanted the dowels to be, and a 6mm hole was drilled into the block and partway into the other half. Wooden dowel pins were then cut down and a small section glued back into the top of the hole to fill it back up with wood before turning. When the pattern is then split open, the dowels can be inserted into the top section of the pattern to allow for alignment. Now, I did have to turn the end of the dowels down slightly to just below 6mm so that it would fit nicely into the holes and allow the pattern to come apart easily. A wooden block with tapered sides was glued to the cylinder to create the steam chest, and the joins were filleted with wood glue to allow it to pull cleanly from the sand mould. The hole at the top is to allow a riser pattern to be inserted, which will feed the casting with hot metal as it cools to prevent sinkage within the cylinder. A gating pattern was made from some aluminium tube stock, and the cutout was milled to match the shape of the pattern extension, and a hole drilled to fit a tapered pouring sprue pattern where the molten metal would be poured. The hot metal will run around the gate and into the cylinder cavity, filling the mould. After the pattern has been turned, it can be easily split open with a knife or a screwdriver. And here was just an example which was glued together with superglue, but I think you'll get the concept. I didn't shoot any video of making the pattern, but it certainly makes a mess of the lathe. To make a mould, I firstly needed a casting flask, so this was simply made from scrap wood and connects together with some steel locating pins. The lower section is called the cope and the upper section is called the drag, but I have no idea why they have these names. The baseboard is sprinkled with talc to prevent the sand from sticking, and the patterns can now be positioned in the cope. These are also coated with talc to prevent them sticking and allow for easier removal from the sand. Now it's important to get the cope the right way round so that the pattern will be on the top side of the cope. Don't ask me how I learned this lesson. Now the sand I'm using is called Petrobond, which is an oil bonded casting sand and is capable of reproducing a high level of detail from the pattern. I use this rectangular sieve to apply a fine layer of sand over the top of the pattern. I did try the sieve from the kitchen, but it was far too fine and I struggled to get the sand to go through, but this little basket is just perfect. It's the sort of basket that you get your chips served in when you have a meal at a pub and is much coarser than the kitchen sieve. Though I must say, my wife did complain that the peas tasted gritty when we had our tea that night. Once the fine layer of sand has covered the pattern, further sand can then be added. This is firmed up with my fingers and then more sand added. This can then be rammed up with the handle of my mallet, which was actually made by my son Oliver when he was at engineering college and is the perfect tool for this process. It's important to ram up around the edges and into the corners and then work towards the middle to keep the sand compacted around the pattern. The mallet can then be used to ram the sand hard down. The excess sand is then scraped away to ensure you have a flat bottom on the cope. The baseboard is used to allow the cope to be turned over without any part of the pattern falling out from the sand in the process. The cope is then flipped over, ready to add the other half of the pattern and the pouring sprue and the riser. Again, a layer of talc is applied to prevent the sand from sticking, and also so the flask will separate easily at the parting line. The other half of the pattern is also dusted with talc and then mated with the other half, and the pouring sprue and the riser fitted to the patterns. The other half of the flask, the drag, is then placed over the cope, and the process of filling the flask with sand is repeated. The riser and the sprue can now be removed and the surface levelled. I find using talc on the holes helps to stabilise the sand so that no grains become loose while pouring and being introduced into the metal. Okay, so a bit of luck. The drag is then carefully lifted away from the cope, and now you can see the importance of the dowel pins to be able to separate easily so that the top of the pattern doesn't pull from the sand. 2 moulds. Some lifting screws were then fitted to the pre-drilled holes, and the pattern is gently tapped to loosen it within the sand. The edges of the pattern are brushed to remove any sand that's crept in between the split pattern, so that it doesn't break out any of the sand when lifted. Once the pattern feels loose in the sand, it can be carefully lifted out. Hate that bit. And I must say, this is quite a nerve-wracking part of the process, as you can easily damage the mould if it isn't lifted cleanly. There we go.
was the scary bit.
The other half of the pattern is then removed and the sand core is added to the core print to allow a hole to be formed in the finished casting. I will explain how this is made later in the video. The cope and drag can now be assembled in readiness for the pouring, but first I need to add an extended riser to increase the volume of metal feeding the casting as it cools. I made a simple moulding jig to make these. I'll just make another one for the other end. To make the sand core, I used some plastic conduit, which was cut into two. This was reassembled into a jig, which I saw on Myford Boy's channel, and it works really well. A quantity of kiln-dried sand was measured out, plus a little extra was added to allow it for it being rammed down into the tube. I used this two-part epoxy resin as the binder for the sand core, as I had seen a video from Mark Pressling where he used this technique very successfully. Now you don't need much epoxy, and the tub looks fuller than it is, as there is already some hardened epoxy in the bottom. This was mixed and then added to the sand until the right consistency was achieved, where the sand will hold itself together without being too wet. The core mould was then filled and rammed into the conduit to remove any air pockets. Now the usual method for making sand cores is using sodium silicate mixed with the sand and then hardened using CO2 gas, but I don't have this setup, so opted to try the epoxy way. And I find it works well with aluminium at 750 degrees, but not sure how it would perform with higher temperatures such as bronze or brass. And of course the other downside is you need to wait for it to cure before removal. The sand does tend to stick to the conduit, but some gentle persuasion frees it from the mould. Any excess sand caused by the split line can be easily scraped away. The core is then coated in graphite powder, which helps fill any minor voids in the sand and also acts as a refractory during the pour. The furnace is a nice compact unit which runs off a domestic power supply and is rated at 1.4 kilowatts, and its maximum temperature is 1100 degrees C, which is hot enough for brass, copper and bronze. It has a PID temperature controller which will automatically raise the temperature to whatever is set on the panel. These seem to be fairly generic Chinese furnaces and are available at varying prices, so do shop around for the best deal. Mine came with a 3 kilogram graphite crucible, a pair of tongs for handling the hot crucible, and some leather heat resistant gloves. The only problem I've found so far was that the paint finish on the lid melted and stuck to the ceramic top part of the furnace during first use. Now the crucible is plenty large enough for small engine castings, with a 50mm hole at the top and 170mm in length. The actual volume of metal at 75% full, as recommended by the manufacturer, is approximately 125mm by 50mm diameter, which is actually quite a hefty chunk of metal. Now this here is a brand new crucible which I have bought, and this is the one which came with the furnace after 18 aluminium melts, and as you can see it has become quite pitted as the graphite has degraded. So the new crucible was bought in readiness to replace this, as it is a consumable item. But I reckon it's still good for a couple more pours yet. I weigh out the approximate metal required for the casting, including the sprues, and load this into the crucible. It's important not to drop the metal into the crucible, but rather slide it in on an angle so that it doesn't impact the bottom of the crucible, because these things are super fragile. Remember, it's made from the same stuff as the lead in your pencil. The furniture was loaded and the excess metal put to one side to be added later. The controller is set for 750 degrees C, which is about 100 degrees higher than the melting point of the aluminium, but you do need it quite fluid to be able to pour. It takes about half an hour to reach the set temperature, and while I'm waiting I can get set up outside ready for the pour. Now you'll notice that the riser on the right is darker in colour, as I used Petrobond, which has already been used several times, and it takes on a distinctive darker brown. Once the furnace has melted the aluminium, then the remaining pieces can be added to the mix, and these are gently lowered into the molten metal. After about 20 minutes, the entire quantity of metal is now a liquid, and after a gentle stir with a graphite rod, ensures that there are no solid metal pieces under the liquid surface. The top surface of the molten metal will have some oxidisation, and this is scraped up with a spoon and discarded, leaving a shiny top to the metal. Then, with my full safety gear on, I can now lift the crucible out and make the pour. Any excess metal left in the crucible is then poured into ingots in a muffin tray, ready to go back into the melt pile. The cooling of the casting causes the metal to shrink, so to prevent this, the feeder continues to supply the casting with molten metal, and you can see this happening on the top of the sprues as the metal collapses in. After a few minutes, the ingots have solidified and are quenched in the water. After about 10 minutes, the flask can then be opened and you get to see if the casting was successful. All looks good here. Now you can see the remains of the sand core still inside the flask. The sand core can then be removed with a screwdriver, and all that remains is a soft slushy mess. Like I said before, I don't know how these resin cores would stand up to hotter metals, but they work extremely well with aluminium. Any burnt sand is cleaned off and the casting inspected. The core has left a nice clean hole through the cylinder, and other than a little bit of flashing at the parting line, the casting looks great. The metal was poured in through the tapered sprue and into the ring-shaped gate and filled up the cavity around the core and up into the riser, or the feeder as it's also called. You can see how the top of the feeder has collapsed down as the cooling occurred. Without this, I was getting shrinkage defects on the casting itself. The gate and the riser were then cut off, and these can go back into the melt pile. So there is the finished casting. I was a bit overzealous with the hacksaw, as I slightly cut into the top surface, but this will be machined away later. This can now be held in a 3-jaw chuck by the extension piece to allow the front to be faced off and the bore machined 2-dimension. The extension will then be sawn off and remounted in the lathe for facing the other end. And, in true Blue Peter style, here's one I prepared earlier. So, what am I going to do with this? Well, it's still a work in progress, but I have mocked up this simple engine frame, and I've also been busy casting some flywheels from a 3D printed pattern made for me by a good friend who posted it out to me. So that will be the basic arrangement of the engine, possibly with a further axle support on the outside. I also mocked up a mirror image of the chassis, as I may also make a double-cylinder version of this little engine. The possibilities are, well, maybe not endless, but certainly varied. Now, the flywheels are cast in aluminium and will probably be fine, but to be honest, they are a little bit on the light side. So to get the flywheels a little bit heavier, I've invested in an ingot of zinc alloy ZL12 from Artisan Foundry here in the UK. This is also known as Zamac in some parts of the world. This is 12% aluminium and the rest is zinc. There's also about 1% copper in the mix. Now this is about 2 times heavier than the aluminium, so should give better weighted flywheels. It also melts at a lower temperature than aluminium, so should preserve my crucibles for longer. Anyway, that is just about the end of this video, about my journey into the exciting world of metal casting. And this certainly opens up many new opportunities to create new and unique parts for my model engines. If you enjoyed this, please consider buying me a coffee at ko-fi.com. The link is in the description below and is always appreciated. And as always, thanks for watching. Well, that was the end of the video, but during the course of the editing, I did get the opportunity to cast one of these flywheels with the zinc alloy, and as you can see there, that is 91 grams, and that is the aluminium one, and this is the zinc alloy one, and it is 200 grams, absolutely perfect. So that's like, well, it's at least double the weight of the aluminium flywheel, and you can really feel quite a difference actually. So yeah, nice metal to use. Anyway, thanks for watching. Bye.